This video shows solutions to compound inequalities. Check how these type of inequalities are solved here in Mathematics of Engineering. Compound inequalities are the type which would have two inequality symbols. That is, there are three terms in one inequality. There are also cases that they are two separate inequalities connected by an and or an or. For the example, 4 is less than or equal to 2x, which is also less than or equal to 7. The first inequality involves 4 as less than or equal to 2x. The second inequality has 2x as less than or equal to 7. The first example has 6 as less than x plus 3, which is less than 10. Simplify the middle term by subtracting 3, and get 3 as less than x, which is less than 10. This is illustrated graphically as two hollow dots on positive 3 and 7. Analyzing the inequality, x comes between 3 and 7, so the two dots are connected. In interval notation, we can write these as an open parenthesis with 3, then 7, and a closed parenthesis. The second example is 4 less than or equal to 2x, which is again less than or equal to 7. 2x needs to be simplified, so we divide 2 on all terms. Then the outcome is 2 as less than or equal to x, which is again less than or equal to 7 halves. Graphically, we can show the inequality as two hollow dots on both positive 2 and 7 halves. The inequality also shows that x is between 2 and 3.5, or 7 halves, so the range connects these two dots. Using interval notation, we place an open parenthesis with 2 paired with 7 halves and a closed parenthesis. Example 3 has 4 as less than x over 5, which is also less than 6. Isolate x by multiplying the middle term by 5, which would also mean that we need to multiply the two other terms too, making the inequality 20 as less than x and also less than 30. With x as greater than 20 but less than 30, we can draw these as two hollow dots connected together. In interval notation, we write an open parenthesis with 20, then 30 with a closed parenthesis. The next compound inequality is negative 3 as less than or equal to a quarter of x minus 1, then this is less than 0. Simplify the middle term by adding 1 to all terms. Then have negative 2 as less than or equal to x over 4, which is less than 1. Next is to multiply 4 in each term, to have negative 8 as less than or equal to x, which is also less than 4. As x falls between negative 8 and positive 4, we can illustrate the answer as a filled dot on negative 8 and a hollow dot on positive 4, and they are connected together. In interval notation, this can be written as an open bracket with negative 8, then 4 with a closed parenthesis. For the fifth example, there is 0, which is less than or equal to x minus 6 upon 2, then this is less than 2. If 2 is multiplied in each term, the denominator on the middle term will be eliminated, resulting to 0 as less than or equal to x minus 6, which is also less than 4. Next is to add 6 to remove the constant with x. This will give 6 as less than or equal to x, which is less than 10. Graphically, this is shown as a filled dot on 6, then a hollow dot on 10, and they are connected. In interval notation, x is at the range of 6 inclusive and 10 exclusive. Example 6 includes two separate inequalities connected with and. They are 6x minus 3 as less than 9 and 2x plus 7 as greater than or equal to 3. Evaluate the left inequality first by adding 3. This makes the inequality as 6x as less than 12. Divide both sides by 6 to have x as less than 2. The other inequality is simplified by subtracting 7, which makes it 2x as greater than or equal to negative 4. Then take x by dividing both sides by 2, arriving at x as greater than or equal to negative 2. We can draw the two inequalities separately, that is, having a hollow dot on 2 and the arrow points to negative infinity. The second inequality marks a filled dot at negative 2 and an arrow pointing to positive infinity. Now, how do we connect the two inequalities? Let's get back to the equation stating and. From set theory, remember that and denotes intersection. So take the common range from the two number lines, and that would be from negative 2 inclusive to positive 2 exclusive. Also for the interval notation, we have an open bracket with negative 2 and 2 with a close parenthesis. For the 7th example, we work with two separate inequalities connected by an or. Start simplifying the first inequality, that is by subtracting 5 and have negative 3x as less than or equal to negative 6. Divide each side by negative 3 to get x as greater than or equal to 2. The second inequality is simplified by subtracting 8 to have 2x as less than or equal to negative 3. Then isolate x by dividing 2 to have x as less than or equal to negative 3 halves. In graph, we draw the first inequality to have a filled dot on positive 2 with an arrow pointing to positive infinity. The second graph has a filled dot at negative 3 halves and an arrow pointing to negative infinity. Notice that the two graphs are separate. How do we place them in one answer? Again, check the connecting word for the two inequalities. The problem uses or, and from set theory, this means union. Thus, we can place the two separate dots and arrows in one graph. Then the interval notation is written as a parenthesis with negative infinity and negative 3 halves in a bracket. Then this is in union with an open bracket with 2 and positive infinity in a close parenthesis.